Let's analyze the specific case of the integral of an inverse square radial field over a surface, a closed surface. So the inverse square radial field is this particular vector field. The reason it's called an inverse square radial field is because, first of all, it's a radial vector field, and second, the magnitude of this vector field at a point x, y, z is 1 over the magnitude of the position vector x, y, z squared. Right. So if you just take the magnitude of this, the magnitude of this vector in the numerator is, of course, the square root of x squared plus y squared plus z squared. This scalar that we're dividing by is this exact same square root, but to the power 3/2. And so when you simplify the exponents here, you get this square root squared. Sorry, I made a mistake here. So this over 2 shouldn't be here because I wrote the square root explicitly. So it's cubed, but then when you so there's one factor of the cubed root here. There's 3 factors. There's 1 factor of the square root in the numerator. There's 3 factors of the square root in the denominator, and so when you cancel them, you get 2 factors of the square root in the denominator, right? So this magnitude and this square root is exactly this magnitude, right? So this is not just some random example. This kind of inverse square radial field shows up in physics a lot. So, like in electromagnetism, the electrical field induced by a point charge is given by this vector field, maybe with a minus sign, depending on what your sign convention is for your, or depending on the charge of depending on whether the charge is positive or negative. There might be a minus sign in front of this. At any rate, what we're going to do is figure out what is the integral of this vector field over a closed surface. And there are 2 cases to think about, right? So first of all, maybe it should make you a little nervous that I haven't said anything about which closed surface. That's a bit strange. But because we don't know anything about the surface, we can't actually just compute this surface integral. That's going to be hopeless. We don't know enough to parameterize the surface. But since it's a closed surface, I hope that makes you think, well, maybe we could use the divergence theorem to evaluate this. So let's calculate the divergence of this vector field. I'll leave this as an exercise, but the divergence of this vector field is actually 0. Okay. At any point where the vector field is defined, so we have to be a little careful about this because this vector field is actually not defined at the origin. So this is everywhere except at the origin. Right, at the origin, it's undefined. So at the origin, the divergence of f is undefined. So actually, right, we were hoping to use the divergence theorem, but if our surface encloses the origin, well, we can't use the divergence theorem because divergence is undefined at the origin. So that's why we have to split this into 2 cases. And the 2 cases are whether our surface encloses the origin or not. So case 1, this is going to be the easy case. Our surface does not enclose the origin. Okay, so if our surface doesn't enclose the origin, then the integral over this surface is, well, now we can use the divergence theorem, right? If our surface does not enclose the origin, then our surface is the boundary of whatever volume is inside of it, right? It's a closed surface, and as long as it doesn't enclose the origin, then divergence of the vector field is defined everywhere inside the volume, but, you know, I'm leaving it as an exercise that the divergence of this vector field is 0, and so we're integrating 0 over whatever the volume is, and so we get 0. Okay, so if our surface does not enclose the origin, then this surface integral is 0. So for our second case, of course, is where S does enclose the origin. Okay. So we have some surface, some closed surface that encloses the origin like this. Now we're going to have to evaluate the surface integral manually, so to speak, as a surface integral because we can't use the divergence theorem. Okay. The problem, of course, is that we can't evaluate the surface integral directly because we don't know what the surface is, so we can't parameterize the integral. But the divergence theorem is actually going to come to the rescue still. So here's the surface S. Since it encloses the origin, we can pick a sphere of some tiny radius that fits completely inside of S and is centered at the origin. So let's call this S1. So S1 is a sphere centered at the origin, so centered at the origin with some small radius. So let me call that S sub r, actually. R is going to be radius. Sphere with radius little r. Okay. All right. So now we can go ahead and so what was the point of introducing this sphere? The point of introducing this sphere is that S together with this sphere, and so normally we would orient a sphere outwards, right? But the whole point of this inner sphere is to sort of cut out the origin, right? The origin is the part preventing us from using the divergence theorem. And so we've surrounded this problematic point with this sphere, S sub r. So if we take S minus S sub r, right, normally we orient this S sub r outwards. So the point of this minus sign is to be orienting the interior sphere inwards instead of outwards. S minus S sub r is the boundary of a volume now, the volume in between, right? So V is the volume in between our surface S and the sphere S sub r. Okay, so the integral over S of f dot n d sigma minus the integral over S sub r of f dot n d sigma. Now we can use the divergence theorem over this volume. So now we're integrating over the volume the divergence of f. But remember that as long as we don't include the origin, the divergence of f is 0. And on this volume, because we've sort of surrounded the origin with this sphere, this volume doesn't enclose the origin, or doesn't contain the origin. So this is 0. So what this tells us is that the integral over our surface, which remember we don't know anything about what this surface is except that it encloses the origin, the integral of the vector field over our surface is equal to the integral over this sphere of radius r, where r is some number small enough to fit our sphere inside of the surface S. Okay. Well, this is going to make things a lot easier because, well, first of all, now we have a particular surface in mind for our surface integral, and second, it actually makes things very, very nice. Okay, so now let's write down the surface integral. What we're going to do is write down what the vector field f is and what the normal field is without actually parametrizing the sphere. So this is still an integral over our sphere of radius little r, d sigma. We're just going to write out what is f on this sphere. So f is x squared xyz over, well, remember what we had in this denominator was x squared plus y squared plus z squared to the 3 halves, but x squared plus y squared plus z squared, that's the over on the sphere, that's the square of the radius. So we have the square of the radius to the power 3 halves, and that's going to be r cubed. Okay, dotted with our normal vector. Well, what is the normal vector for a sphere? A normal vector for a sphere, right, at whatever point you're at on the sphere, the normal vector is pointing in exactly the same direction. So if this point is x, y, z, the normal vector is x, y, z. Except we need to make sure that it's unit length, so we have to divide this by the magnitude of x, y, z. Right? So that's a nice shortcut to get a normal vector for a sphere. Okay, so for our normal vector, we're going to use x, y, z divided by the length of x, y, z, but we're on a sphere of radius little r. The distance of this point on the sphere from the origin is little r, so that's little r right there. Okay, so we're getting the integral over s sub r of, now in the numerator, we get x squared plus y squared plus z squared over, and then in the denominator, it's r to the 4th. So d sigma. But look, x squared plus y squared plus z squared, that is, that's r squared, again, because we are on the sphere of radius r. So over r to the 4th, d sigma. And now this simplifies. Integral over s sub r of 1 over r squared, d sigma. But remember, r is the radius of this sphere, right? R isn't a coordinate. It's not, we're not doing an integral with spherical or cylindrical coordinates. R is just the constant radius of this tiny sphere that we're using. So this 1 over r squared, we can move that outside of our integral. We're integrating over this tiny sphere of radius r, d sigma. But when you integrate d sigma over a surface, you get the surface area of that surface. And we know the surface area of a sphere. It's 4 pi r squared. And then, well, then the r squareds cancel and you get 4 pi. Okay, so what we found, right, remember what we were doing was finding the surface integral over any closed surface that encloses the origin. So what we found was, right, 4 pi is the integral of this inverse square vector field over any closed surface S that surrounds the origin. Surrounds origin. Okay. So this inverse square vector field, when you integrate it over a closed surface, you get either 0 if your surface does not enclose the origin, or 4 pi if it does enclose the origin.